Today, we want to remind ourselves of what we've been up to before spring break happened. We've been looking at patterns of repeated addition and patterns of repeated multiplication, which means that we've been looking at linear functions and exponential functions. We've been looking at them in many different ways. And what we're building towards is understanding things using the rule of 4. So understanding, taking a concept and understanding it as numerically, understanding it verbally, understanding it analytically, and understanding it graphically. So in the case of addition, patterns of repeated addition and multiplication, linear and exponential functions, looking at a table and identifying a pattern, describing that pattern with a sentence, translating that sentence into an equation, and then we haven't added the graph piece yet, but it's a coming. The big idea is we want to understand how each of these things is related to the others. So with a table, we want to be able to write a sentence. With a sentence, we want to write an equation. That has typically been the direction that we've been going. But we also want to be able to look at an equation and write a sentence, or look at an equation and produce a table of values. Or we want to be able to take a table and produce an equation. And then we want to add graphs into this mix, which is the part that we haven't got to yet. So how are the graph and the table related? That's going to be the most direct one. When we're looking at an equation, what kind of graph does that produce? And how would we write a sentence describing what we see in a graph? So it's not just being able to take one and write the other. It's about understanding how changes in one will affect the others. So how do changes in the table alter the sentence? How do changes in the table alter the equation? How do changes in the equation alter the graph, and so on? So we want to, the rule of 4 is about describing things, understanding a concept in 4 different ways, and how those 4 things are related. So let's look at some examples. We can go all day just asking specific questions and then asking and answering specific questions. But to me, the importance is in the differences from one problem to the next. The important differences happen from one problem to the next, not what happens in each individual problem. So for example, let's look at a table. And let's start off with 0, 10. And then at 4, we'll go to 20. Right now, not enough to make a judgment on what kind of pattern we're dealing with. But if at 8, we end up at 30, now we have pretty strong suspicion of what the pattern is. And then if at 12, we end up at 40, we have very strong evidence as to what's going on. We see that the pattern down here, going from 10 to 20, from 20 to 30, and from 30 to 40, it looks like we have a pattern of repeated addition. We are adding 10 a bunch of times. It also looks like up top we have a step size of 4. We can pick any one of these points as a starting point, but if 0 is available in the x, that's a great starting point. So we could write a description for what's going on in this table of values. We could say y is 10 when x equals 0, and y is increasing by 10 every 4 units. So we have a description about where things start. Y is 10 when x is 0. How y is changing, y is increasing by 10, and how often we make that change, every 4 units. And we can translate that into an equation. We could say this means that y is equal to starting off at 10 and adding 10 every 4 units a bunch of times. We would simplify 10/4 to 5/2 or 2.5 or 2.5. But we want to make sure that our equation, our table, and our sentence are all saying the same thing. So we could simplify. We could simplify the slope here, and we could write y is equal to, starting off at 10 still, and then 10/4 is 2.5, so plus 2.5 times x. Start off at 10 and add 2.5 every unit, or 2.5 a bunch of times. If we rewrite the equation in this way, we might rewrite our sentence to reflect these changes. Y is equal to 10 when x equals 0. And y is increasing by 2.5 every 1 unit. Because the slope is what happens every 1 unit. This might produce a different table. This equation we could use to write a table about what's happening, not from 0 to 4 to 8 to 12, but what's happening in between 0 and 4. So we could start off at 0, 10, like we did before, but now we'll add 2.5 every 1 unit. So we're just looking closer at what's happening between 0 and 4, as we're adding every 1 unit we're adding 2.5. So this is all looking at the same function, a bunch of different ways of looking at the same function. We could also think about reading this equation in the weird way, because if I want to change this plus 10 to, say, a different operation entirely, then I don't get to move the dividing by 4 under the 10. So let me change things just a little bit. So it's all about how things change when we want to write a new equation. So in a new equation, if I say start off at 0, 13, and then go 3, 23, 6, 33, and 9, 43, some things have changed and some things have stayed the same. I've changed where things start. I have not changed how y is changing. But I did change how often we're making that change. So when I go to write an equation, I'll say y is equal to 13 when x is equal to 0, and y is increasing by 10 every 3 units now. y is 13 when x equals 0, and y is increasing by 10 every 3 units. So really there's 3 things that we want to look at for a linear function. Some starting points. Sometimes we get to use the y-intercept, like in these examples. A rise and a run. Too often we say a linear function just has 2 things, a slope and a y-intercept. But that slope has 2 parts to it. Let's make another change to what's going on in our function. Let's suppose that we start 0, 13, but then at 3 units, instead of being at 23, it's up at 26. Right now, not enough to make a conclusion about what's going on. But then let's suppose at 6 units, we are up to 40, 12. And then at 9 units, we're up to 104. Now we're not just adding 13 a bunch of times. We didn't add 13 3 times, because from 26 to 52, we added 26. And then from 52 to 104, we added 52. So the starting place, 0, 13, I still want to start off with 13. That seems lucky. Good choice for a Monday. But now the operation has changed to multiplying by 2. Our interval is still the same at plus 3 units. Now when I want to write an equation, instead of where I wrote plus 10 before, I have to write times 2. So I say y equals, we started off at 13, and then the 13 got multiplied by 2 a bunch of times. But to indicate repeated multiplication, we use an exponent. And I can't just divide the 2 by 3 like I did with the slope, because it's not addition, it's multiplication by 2. So I have to raise this to the x over 3 power. Oops, this is the right color for 3. So remember, the 2 to the number of steps, and the number of steps is counting by 3s. So 1 step is a 3, so x divided by 3. When x is 6, 6 divided by 3 is 2. We've multiplied by 2 twice. When x is 9, we've multiplied by 2 3 times. This is like the strange way we interpret the equations from the slope from before. If y is equal to 13 plus 10 over 3 times x. Another way to write this, kind of thinking it in these terms, instead of adding 10/3 every 1 unit, we can write this as 13 plus 10 a bunch of times, and we can multiply by the number of times that we add 10. And so really when we see that x increase, the change in y happening every 3 units, we want to replace the x with an x over 3, and then that will count the number of steps. We have the advantage in a linear equation in that we have 10 times x, and then the x is divided by 3. I could write this as 10 divided by 3, and then multiply the result by x. This is because division and multiplication, the way they interact. But this is an exponent, so I raise to the multiply by 2, and then we divide by 3, and then make that the power of 2, and I can't just change the order there like I can with multiplication and division. Either way, we can write an equation. It's the weird way we write things. We can summarize what's going on in this in the same kind of way. We can say that y is equal to 13 when x is equal to 0. And then we can summarize y, or we can describe what's happening to y. Y is multiplied by 2 every 3 units. So we have the numbers that create a description. This is a description of what's going on in numbers or a table. Here's a description of what's going on with an equation. Here's a description of what's going on in words with a sentence. And the structure is very similar because it's a pattern of repeated addition or repeated multiplication. Any questions? One interesting variation on these patterns of repeated multiplication is when we have a multiplier of 1/2. That one's an important one for us. And this is something that we're a little more familiar with in a term that we're more familiar with, especially ever since we entered the atomic age. So we see something's happened every 4 units. We can see that we're starting off at 0, 100. And we go from 100 to 50 to 25 to 12.5. So we're multiplying by 1/2. We should note that multiplying by 1/2 is the same as divide by 2. So y is equal to 100 when x equals 0, and y is multiplied by 1/2 every 4 units. So we can write an equation. Y is equal to 100. And then we multiply by 2 every 4 units. Numbers, sentence, equation. All different ways of saying the same thing. The reason I wanted to do this example is that we have an interesting multiplier. A multiplier of 1/2, we like to reference something called a half-life. A half-life is the interval that will give us a multiplier of 1/2. So we could say y is equal to 100 when x equals 0. And specifically because it's multiplied by 0.5, we could say y is equal to 100 when x equals 0. We could say y has a half-life of 4 units. So we could describe a multiplier of 0.5 with the phrase half-life, but it's still conveying the same information. So half-life is something that the most common example would be like when we talk about radioactive material. Radioactive material is decaying faster when there's more of it. So as it decays from being radioactive to being inert, it starts to calm down a little bit when there's less of it there. So you start off with 100 grams and you have a half-life of 4 years, let's say. After 4 years, 50 grams of it is still radioactive. But the other 50 grams is going to decay into something else. It's more complicated than that. We're just trying to put some numbers on what we describe. Any questions? So this is what we want to focus on. We want to look at patterns and how we describe patterns of repeated addition or patterns of repeated multiplication. Right now, all I want to be able to do is put up a table, a sentence, or an equation, and have y'all write down a table, a sentence, or an equation. Whether I use a pattern of multiplication or a pattern of addition. All right, that's going to do it for today. Welcome back from spring break, everybody. I will see y'all on tomorrow, and thanks for playing.